like to introduce Jonas Nycander, who's here from Stockholm University, who is a professor in the Department of Meteorology. He's visiting in Princeton in the GFDL lab, so we're not quite as far away as Stockholm right now. He's had his training in engineering physics, I guess, and done a number of studies. What brings him here today is interested in ocean circulation, and I'm particularly interested in this as it affects the sediments that are accumulating on the bottom of the ocean. But he also has many other issues, interests, including, I guess you modeled vegetation and CO2 and warming kinds of problems, and the Miocene in the Arctic, also of great interest, and you have a position on the carbon tax also. So we can wade to all sorts of things. So I'll introduce our speaker.
Yes, so I will be here today in the afternoon if someone will talk to me. Yes, so I will be here today in the afternoon if someone will talk to me also. And the main interests I have are, I would say, oceanography, ocean circulation, and internal tides in the ocean, but general ocean, physical oceanography, and also some recent interest in coupled climate modeling if someone wants to talk about that. But today I will speak about tides, and especially internal tides, which are then internal waves excited by tides. And they are, as I will mention briefly here, they're a key process controlling the deep circulation of the ocean. And so I'm from Stockholm University, Department of Meteorology, and also we have there a center for climate research called the Bolin Center. Okay, so yes. So to motivate why we should be interested in internal tides, I will start with a very simple, oversimplified sketch, I would say, about the vertical circulation in the ocean here. So we have the pole here, the equator here, and the overturning, the sort of vertical circulation works like this, that you have, let's start here, for instance, in, let's say, the North Atlantic, where deep water is formed by cooling at the surface. This cold, dense water sinks to the bottom, and then flows along the bottom of the world ocean, and then returns by a very broad upwelling like that. Okay. Now, you might ask, what forces, what drives this circulation? And I would say, in general, for the ocean, I mean, many have the picture that, okay, the buoyancy force is important. Maybe this is forced by buoyancy forces at the surface. Now, from a strictly theoretical perspective, that's not true. Of course, buoyancy is important, but what actually drives this flow isn't the buoyancy here at the buoyancy flux at the surface, and you can show that by something called Sunstone Theorem. I mean, a century ago, this Swedish oceanographer Sunstone realized this, and he did some speculation and some very simple lab experiments. And what he showed was that if you have only buoyancy forcing at the surface and no mechanical forcing, you get a very weak circulation. And the only way, and you get also more or less homogeneous water in the ocean below a thin boundary layer. And the reason is that molecular diffusion is too weak to get down the heat into the ocean. So if there were only buoyancy forcing at the first surface, you would have a more or less homogeneous and stagnant ocean, and there would be only a thin boundary layer in the tropics where it was warmer then. And eventually all the whole world ocean would be filled by this cold and dense water. Okay. So the circulation is fundamentally mechanically forced. And there are, of course, the main forcing, I would say, is wind forcing. And so the circulation, which is not the wind-forced adiabatic, so more or less adiabatic circulation in the thermocline up here, is not shown in this picture. So that's one external forcing, wind forcing. The other one, and that's what's shown here, is this deep overturning. That is essentially forced by mixing here. So it's actually the mixing of this broad upwelling here that warms this upwelling water and makes it possible to make room for this dense water to replace it and coming from north like that. So fundamentally, this deep circulation is forced by mixing. Now there is some disputes of where is the boundary between this sort of wind force and this deep force. Maybe this boundary is actually pretty deep, but for those who know about the water masses of the world ocean, The bottom, the densest water down here is called Antarctic bottom water, and that is definitely, that circulation of that is definitely forced by this mixing. Okay. So that is the main interest of mixing and internal tides in the ocean, because it's actually a key ingredient that forces the deepest circulation. Okay, so where do these internal waves come from then? Well, in principle they could be excited by winds, and they could also be excited by tides. Now, for a long time, it was believed that most of the tides are dissipated on the shelves. And it wasn't until maybe 30 years ago or 20 years ago that people were starting to think that perhaps tide could actually be important also for in the deep ocean. And the reason why people were only considering tides on the shelves for a long time is that, well, we're thinking of then the usual turbulent mixing, and that is increases very strongly with the bottom flow velocity. And so the usual quadratic bottom drag force. And if you use that scaling, almost all mixing is on the shelves. On the other hand, you could also have another mechanism, which is excitation of internal waves by bottom topography. But no one knew how strong that would be. But maybe some early signs that could be important came from this kind of work, which illustrated here by a figure from a paper in Science, which is quite well known in year 2000 here. So these people did here, they ran a tidal model with inverse, a kind of inverse model here, where they ran a tidal model which assimilated altimetry observations by altimetry satellite observations from space. And so in this inverse modeling basically means that you have adjustable parameters in the model that you fit to you use to fit the output of the model so that it fits the observations from satellites as well as possible. And what they found was that to make the best fit, they had to put a lot of dissipation into the deep ocean, not in the shelves, right? That's what's shown in this picture here. So this is a sort of a map of the dissipation that was needed to match the satellite observations here. And what they found was that perhaps 25% of the total mixing occurs in the deep ocean. So that was a surprise to many, and of course excited the interest of oceanographers. And here is another historical, very important piece of work that led to the interest in these internal tides. This is a measurement campaign in the Brazil basin in the South Atlantic by a large group of people and headed by Kurt Polzin. And so what they did was to measure the dissipation and by something called microstructure measurements. So they measure velocity shear on the millimeter scale in the ocean with an instrument that they sink then to the bottom of the ocean. And from that they can infer turbulent diffusivity. And so these are then profiles of turbulent diffusivity measured by this microstructure instrument. And here is a profile then across the the Brazil basin. And what was so striking here, of course, is that what is shown here is the bottom topography along this track. And there is very much larger diffusion above this rough topography in the eastern part of the basin than in this plain part, over this plain in the western part here. And this rough topography, this is on the western flank of the mid-Atlantic ridge in the South Atlantic here. So there is a lot of small ridges and canyons coming down here from the mid-Atlantic ridge, while on this part the bottom is very flat. And so, of course, this doesn't directly tell what causes this, but the immediate guess was that, the main flow you hear, this is just in the middle of some mid-Atlantic gyre here. There is no strong currents really here except for tides. So the first guess would be that this strong mixing is caused by internal waves excited by tides. That's a natural conclusion. So then in a very well-known paper, Monk and Wunsch here in 1997, they put pieces together to try to get a kind of a simple global estimates of how this works. And so, and to get estimate of the energy needed for this process here. So if you assume that this deep overturning circulation is forced by the mixing, they wanted to estimate how much energy is needed for this mixing. And so what they used is an estimate of the vertical transport 30 swirls here, and basically this comes from observations of deep currents across some key seals, for instance, between Iceland and Greenland and some other key spots in on the bottom of the ocean. So they had estimates of the vertical transport. You also know the stratification, and you can assume that you have a mixing efficiency of 20%. So 20% of the energy in the internal waves they use when they dissipate, they use 20% of the energy to erase this. Sorry. Oh, yeah. That was strange. Yeah. Okay. Put this here. Yeah. So if you use this, they come up with an estimate that 2 terawatts of internal wave power is needed to force this deep circulation. And then they compared this to the total what could possibly obtain from tides. And well, the total dissipation of tides is pretty well known, actually, from astronomical observations of how fast the moon resides from the Earth. At least that is used for the most important M2 component. Anyway, the total dissipation of tides is well known, and if you then say that, okay, one quarter of this is in the deep ocean, that gives you 1 terawatt. So that is roughly half of what is needed to power this deep circulation. So these numbers fit fairly well. Of course, they are very uncertain. I mean, a factor 2 could easily be wrong here, but at least it shows that it's reasonable to assume that internal tides are in fact the key in forcing this deep circulation. And so this is where I started to work on this problem. So what I wanted was to calculate from direct theory and computation the global power of the energy that goes into these internal waves. So this shows the principle of what is happening here. You have these barotropic tidal oscillations here. So the whole water column oscillates back and forth with a fixed tidal frequency omega here, and a fixed sort of given barotropic velocity. And here these blue lines are density surfaces, and when the oscillations are above some hill on the bottom here, then the density surfaces are perturbed, and that creates internal waves that radiates away from topography.
What speed are you talking about in the bottom?
Sorry?
What's tidal current speed? I mean, 1 centimeter a second, or?
Typical in the open ocean, typical speeds would be a few centimeters, maybe 5 centimeters per second, 2 centimeters, 3, of this order. And the typical amplitude back and forth is maybe 500 meters in one direction and 500 meters before it comes back again, something of this kind. Okay, so to solve this problem, we'll use the simplest possible kind of set of fluid equations here. So these are the linearized standard primitive equations here, equation of motion here, incompressible flow, hydrostatic equations, and then vertical advection over density. And you can then use standard linear theory. I mean, these are already linearized, and you can also, if you have a sort of a gentle bottom slope here, then the whole problem, also the boundary condition at the bottom, can be linearized. You apply a radiation condition from above, and you can solve the whole problem. And this was done, I mean, the basic theory was worked out by Bell in 1975, and he came up with this expression here for the energy conversion. So C here is the energy conversion over a certain region. Let's say that you have a square basin or something, so you can easily do a Fourier transform. Then this H tilde here is the Fourier transform of bottom topography, and the whole energy transformation then, or energy conversion over this area, is given by this expression here. Okay.
Is capital N the Weissler frequency?
Yes, N here is the buoyancy frequency, Brunt-Basel frequency. U naught is the tidal velocity. So this is the input you need bottom topography. Here, H tilde, you need tidal velocity and hydrography.
There's no adjustable parameter.
Sorry?
There's no adjustable.
No, there is no adjustable parameter. This is sort of first principle derivation with the linear wave theory. And K is the wave number of the topography. Okay. Now, this is very, I mean, of course, to come up with this expression, you have very simplified and idealized assumptions. For instance, the buoyancy frequency is constant, tidal frequency is constant, it doesn't vary in space. Okay. And if you go, of course, this is not true in the I mean, if you if we would use this for practical calculations, it would be very, very difficult because, well, first of all, the tidal velocity isn't constant over an ocean basin. It varies. Hydrography varies. And if you have a very irregular basin with this, the real shape, it's very difficult to know how to deal with the Fourier transform also. So to circumvent these problems, I decided that it's better to do an inverse transformation of this to real space. Okay? And if you do that, you get this expression instead. Oh yeah, I forgot to say one more thing that is a disadvantage with doing this, solving this in Fourier space, is also that you just get one number here for the whole basin or for the whole area that you're considering. It would be nice to know where in real space this conversion is actually occurring. So that, from all these points of view, it's better to do an inverse transformation to real space, okay, like this. And so I just point out one thing here, that here the non-trivial aspect of the inverse transformation of this is this 1 over k here. Okay. So basically we have a product of different functions here, and a product between 1 over k and this other function here. Well, if you do an inverse transformation in Fourier space of a product, that becomes a convolution. So this convolution, this product with 1 over k becomes a convolution with 1 over r, which is this integral here. Okay. So to calculate then, yeah, you get an expression for the total power here, but now it's an integral of a real space. So that means that we can interpret this integral here, this expression, as conversion per unit area, E here. And that's, of course, an advantage. Now we have conversion in a particular point in space. Okay? And to calculate that, you need now, you basically multiply the local slope here with this convolution integral, which is then, you could view it just as a weighted average of the slope over a region around that point where you calculate. Okay? So you average the slope with this weight factor 1 over r, distance from that point, multiply it with the local slope. And then you need the local stratification and the local high tidal velocity. Okay? So the advantage now is, of course, that this function here decreases away from the point, so it doesn't really matter what, it doesn't have, these coefficients don't have to be constant over the whole ocean basin to use this. You can use the local value, and if it's different far away, it doesn't really matter because, this decays this averaging function anyway. Now there's one more thing, and that is, this is still a very idealized expression which assumes uniform stratification and infinite depth. So I decided that to do something a little bit more sophisticated and try to correct this for the actual finite depth of the ocean. And then I went to some other people who were an article in the literature where people solved the equations with finite depth, and they said that the main effect, what you can find then, is that if you have a finite depth, there is no influence of topography, which is on larger length scale than the maximum wavelength of the internal waves, the lowest internal wave mode. So the longest, if you have a finite depth, there is a maximum wavelength of the internal waves, and beyond that, there is no influence, in fact. You can't, scales larger than that cannot excite internal waves. So then you can go back to this Fourier expression here and introduce a filter here that simply filters away two large length scales here. And if you then do again this transformation, you can see that this means that instead of this function 1 over r, you have another function here, a Green's function, I call it, g here, and which replaces then 1 over r here. And also it turns out that you can do this with the WKB approximation to take into account the vertical variation of the buoyancy frequency, and that means that you then can use, well, it turns out that here you have the bottom buoyancy frequency near the bottom, and in this, well, there is also a filter length connected to this Green's function here. And this plot here shows that the sort of picture of the influence of this finite depth here. So with an infinite depth, you have a Green's function decaying like 1 over r or 1 over x here. With a filter, it decays much faster. So basically this x equals 1 here is 1 vertical wavelength of the lowest internal wave mode. So you basically screen off the influence of points further away here. And now this Green's function is known analytically. Of course, it's an approximate way of dealing with this, but at least you know it analytically, and then you can numerically very conveniently cut off this integral here because it actually decays very fast. So the whole problem becomes very localized with the scale of the length scale of the maximum internal wavelength. And then, so what I did then is to truncate this at x equal to 5, and then calculate this integral here, over the whole global ocean. So the data needed were hydrography here, local stratification, tidal velocity, which both can be downloaded from the various data sources, and also hydrography, h here. So to calculate the conversion energy in one point, you calculate this convolution integral, this averaging around that point. And you need to do this over a length scale of maybe 50, 100 kilometers or something like that. And then you move to the next point and do another integral around that point, and so on. So in this way, it's possible to calculate. Yeah, so here are the input data, topography. All can be downloaded on the internet here. Tidal velocity for people who run tidal models with, again, this altimetry, and stratification. And so the result is this. So this gives in each point here the energy conversion of the topography at that point. How much energy goes into internal waves at that point. Okay. And it's extremely inhomogeneous. The most critical aspect is, of course, topography. So the steeper the slope is, the more energy. And so this is a logarithmic time color scale here. 0 means 1 watt per square meter, minus 3 means 1 milliwatt per square meter. Okay. And you can see clearly topography. You can see all the main underwater ridges here. Here is steep topography. So there's a lot of energy where you have steep topography. There's very little if there's gentle topography.
Now, if you had 2 to 5 centimeters per second of
Yeah.
tidal energy, look at the east coast of Australia, East Australian current.
Yeah.
We've got huge currents, a meter per second.
I mean, these are tidal currents. This is only tidal currents,
Okay.
not boundary currents. This is not part of the calculation. Yeah, yeah. This is. I mean, if you have, you also have some. You can also have internal waves excited by geostrophic flow, like boundary currents or also eddies. But that's a different story. And it's global. People have also tried to estimate that, but that is less. Globally speaking, the tidal energy, the tides give more energy for internal waves. But these lee waves are also important in some regions. But it's not part of what I'm doing here. Okay, so here is what it looks like in this Brazil basin, where one of these, we saw before, these measurements were done something like here, and here is the flat bottom. We have, you can see that it's about 2 orders of magnitude larger energy conversion here over this rough eastern part of the basin than in the western part of the basin. So here you have orders of magnitude maybe 0.01 watts per square meter, and here is 100 times lower. And here, if you integrate it globally, you get some numbers here. Well, for many reasons, the calculations I made here are not reliable over shallow seas, I would say. And I won't go into details, but so let's forget about this total and look at below, for instance, 500 meters depth. And it's, by the way, it's most interesting also for the deep ocean. That's my main interest. So if you look below 500 meters and all tidal components, you get numbers around 1 terawatt, which is pretty good actually. If you compare to these inverse estimates from tidal models, this is just in the right ballpark here. You can compare to the total dissipation to 2.4 terawatt for the M2. If you look just at the M2 tide, I get here 0.8 terawatts, which is about 1/4 of that. Okay, so this is very encouraging then. So in some later work then, I had a graduate student, Said Falahat here, and also some other co-workers to compare these kind of calculations to observations. Of course, I mean, it's nice to have theoretical calculations, but what about the real world? I mean, after all, there are a lot of simplified assumptions in these calculations. It's linear theory and so on. So here are 4 data sets that we used here. So these are the same data that I showed before by Kurt Bolzin and co-workers. They did two campaigns here in the Brazil basin. So the different colors of two different campaigns in 2 different years. So this is by far the most abundant data sets. There are between up to 200 profiles here. Here is another data set in the East Pacific. It's the experiment is called Ladder here, and it's on the East Pacific rise. And the scale, horizontal scale, is very different here. So this is a huge area. This is about 10 degrees longitude across. Here is about 1 degree across. So this is actually a much smaller area, and also a smaller number of profiles. And then these are 2 more data sets, one in the North Atlantic and one in the Western Pacific. And let's not dwell too much on that. There would actually be a lot to say about this, but I will only show very briefly some of the results here. So this is a scatter plot of the results for the Brazil basin. Okay? So on the horizontal axis we have the calculated vertical energy flux with the calculations I showed you before here. Okay? On the vertical axis is the observed dissipation energy from these microstructure measurements integrated over the water column. And then it's a question, how far from the bottom should you integrate? Because when you get up into the mixed layer, clearly this has nothing to do with internal tides. So we try to adjust these to see when you get the best fit. And it turns out that to get the best fit, you have to integrate something like 1,500 meters up from the bottom. I don't remember exactly, but something of this kind. Anyway, so this is the vertically integrated observed dissipation in each station, and for that particular, and this is the calculated energy flux for that particular date, because it varies. You know, you have spring tide and neap tide. It makes a big difference. So these are calculated values here, matched exactly to that position and that date. And as you can see, there is a lot of scatter, of course. These are observations, and these are very kind of turbulent processes and so on. But there is also pretty good correlation, actually. So we were reasonably happy with these results. And also the order of magnitude agrees. So the observed dissipation is about, the observed, you can see that they are on the average a bit below this 1-to-1 line here. By the way, I should mention that this is a log-log plot. Okay. Yeah. So on the average, the observed dissipation is a little bit lower than the calculated one. And if you take the average of that, it's about something like 35-40%, which seems reasonable. I mean, maybe not all the calculated energy goes to dissipation locally. Some maybe radiates away, or there are of course many uncertainties with this. But there is also a pretty good correlation between the individual sites here. So that was for the Brazil basin, and now you can come to another of these data sets in the East Pacific rise. It's called Ladder here. And now it's quite different here. Even here there seems to be some kind of correlation here, but the main thing isn't really that. The main thing is that the observed dissipation is much smaller than the calculated energy flux. So what is happening here is apparently, I should say, and we of course tried to see various factors that could explain this big difference. For example, the calculations were based on linear theory, and we know for sure that this is not valid if the topography if you exceed the critical slope on the bottom. And if you have a supercritical slope, it's actually an open problem. What is the real? You can't use any standard theory, and it's pretty much unknown, the general scaling of what is the energy conversion in that case. Now, I think that actually the energy radiation, the energy conversion kind of saturates when you reach supercritical slope. And if you apply that, that means that, okay, if we assume that it saturates, these black dots here are for the linear calculations. If you do a very crude capping of these values to the supercritical slope, you get to the red dots. And it gets a little less bad, perhaps, but it's still, even if you decrease these calculated values by this capping, you're still far below the observed values. So clearly, I think we can believe these calculated values, that these internal rates, they have to be generated there. After all, we know pretty well that this is the topography, and this is the tidal velocity. But apparently, most of these waves radiate away. They don't contribute to the local dissipation here. That must be what is happening. And it's sort of possible, I think, to understand that from, if you look at the topography here, it's very different. So this was the first set of experiments here. This is a very large extended region of rough topography. There are ridges and seamounts everywhere here. Okay. Here it's very different. It's a few short seamounts, and then it's pretty much flat around it. So I think what is happening here is that since these are pretty much alone, these seamounts, internal waves are created here by tides, and then radiate away and dissipate mostly in other locations. While here, while it's a much higher, there are many reasons why you get better agreement here. But for example, if you have a generally much higher level of internal wave activity because there's rough topography everywhere here, that means that you get much stronger nonlinear interaction, and that would contribute to then to more local dissipation. So that's, yeah. And also, of course, you have incoming internal tides from neighboring topography. So I think it's reasonable to, I mean, it's understandable that you get a much better agreement between the general level of dissipation and the calculated energy conversion in this region than here. So in some sense, I think the results from these comparisons, they give some support to the theoretical model. On the other hand, it also points to really things that need to be solved to go on with this work. We really need to understand, the further propagation and dissipation of these waves, and not just how they are generated. Okay, so yeah, that was the conclusion from this comparison. We have a reasonable correlation in the Brazil basin, 0.66 correlation, which is, well, I don't know if it's good or not, but I'm not very used to experimental data, but from what I hear from people who work with observational data, you can't expect too much, so this is pretty good actually. And on the other hand, we have this big discrepancy for the other side, where you have 50 times more energy calculated and observed, and the reason is probably that it propagates away. And then I will briefly mention some other applications of these calculations I've been doing here. So here is one thing you can do with it is that now, if you go back to this tidal modeling here, that tidal model I showed you with this inverse model, it didn't have any, they didn't put in any internal wave drag there. They found by these inverse calculations that there has to be some wave drag in the open ocean. But then, of course, what you can do is, I mean, you can put, we now have a prediction of how big this internal wave drag should be from these calculations. We can put that into a forward tidal model and to see how that improves the performance of the tidal model. And that was done by this Matthias Gren here, this co-worker. So what he did was he took a tidal model, actually basically the same model that was I showed before here, and he put in three different parameterizations of the drag caused by these internal tides. The calculations I show you here, and also some other standard, more simple-minded parameterizations that are being proposed in the literature here. And both these they are not based on sort of direct calculations of these in internal waves. They're more based on simple scaling assumptions, and they both contain an adjustable length scale here, or a tuning parameter. This L here is a tuning parameter, this gamma here is a tuning parameter. So these are more or less, I would say, rough estimates or hand-waving or even scaling arguments. People have come up with these two proposals, and both contain tuning parameters. In mine, there is no tuning parameter. It's sort of first principle calculations. And so these are the results. So he put these three parameterizations into the tidal model, ran it, and then evaluated the RMS error when comparing to satellite altimetry. And so for this, there was a 7 centimeter error, and then with these other two, there is considerably larger errors here. So this was encouraging, I think. And you can by eye see here actually that the error is actually much smaller than with these. So that's one use of these calculations to improve tidal models. And then I will briefly mention this about sediments, which Roger mentioned here. It's not one of my main interests, but I've been involved at least partly in some work with this, and that was I was contacted by Robert Turnovich, a person who is doing sediment work, marine geologist. And so the idea here is that the internal tide, of course, it means that in the open ocean here, you have basically, in most places, the tide. If there is no strong currents nearby, the tidal velocity is a dominant part of the flow field. And that is, generally speaking, in the ocean, open ocean, too weak to resuspend or excite sediments at the bottom, only a couple of centimeters. Now, if you have topography and internal tides, that adds to the bottom, or in some cases, of course, subtracts. But that modifies the background barotropic tidal velocity. And it could mean, if you have fairly steep topography, it could, for instance, double the velocity. And that may push the velocity over the threshold needed for resuspending sediment. So that's the basic idea. And so here is a calculation illustrating that. And this calculation is done basically with the same code I showed before, the same method. And here, this is the maximum then tidal velocity, where we've added the internal wave contribution I calculate here to the background tide. And background tide is just from a tidal model, which we have downloaded, the same global tidal model. And you can easily see what is what here, because this background tidal model has a resolution of 1 degree, so it varies only very smoothly here. You can see that the background tide is a bit larger in this corner than at that corner. And this is, you can see here, each of these bars here is 1 degree, and here also, so you can see sort of the scale of this. And this is a rectangular area in the North Atlantic, where Robert Turnovich then has done sediment experiments. So you can see the contribution from the internal tides is these sort of small dots here, where you have increased tidal velocity because of topography, some seamounts, and the added velocity from the internal waves. And so in this work, the basic idea is to use isotopes to evaluate sediment dynamics. So thorium-234 is a short-lived daughter of uranium here. Okay? And the half-life of this thorium is about 24 days. And these two isotopes have very different... Yeah, so if nothing is happening, if you just have stagnant water, then that means that the radioactivity of this isotope should be the same as this. There is a kind of a natural equilibrium ratio between the concentrations of these two elements. Now, this thorium attaches very easily to particles, which uranium doesn't. So if there is particles in the water, the thorium is scavenged and it follows the particles down to the bottom here. So that means that you then perturb the ratio away from equilibrium. And that is what was measured in this experiment. So they took sediment, they had sediment traps in the water column and also measured sediment at the bottom. And they could measure then that, so this is a picture here of the topography here. So they have a background mean flow to the right in this diagram here, okay? And they could measure downstream of this, they could measure up at the height of the top of the seamount here. They could measure this sort of disequilibrium, indicating then that there had been a lot of scavenging from sediments, from resuspended sediments. And therefore, there was a disequilibrium in the thorium concentration in here. Whereas if you go above this seamount height, above here, you could see that there was actually equilibrium concentration. So that's shown here. Along this side of this diagram, you have equilibrium, and that is some of the points here, they are from heights above the seamount, and that's equilibrium. And then you can say these points here, they are from heights which are well above the boundary layer. I mean, this big patch here is in the boundary layer. There is natural that you have this equilibrium. But downstream of the seamount, you also have this equilibrium far above the boundary layer. But in water that had, within the last few days, passed by this seamount. So by measuring this disequilibrium, you can sort of have a signature of resuspension of sediments of this seamount. So the idea of this work eventually is to have a method of having a proxy data in the sediment of internal wave activity, and thereby indirectly of tides. I think this is quite an exciting thing to have proxy data in the sediments for tidal activity actually. Yeah, that was it. So, I'm coming to the end here perhaps. So, just some final comments here. There are of course a lot of uncertainties in this method, and perhaps the main ones are, in these global calculations at least, is that actually topography isn't well known on the fine scales needed to accurately calculate this. I mean, in the calculations I see that a lot of the total energy flux is generated by topographic scales below 10 kilometers. Now, the database I used in the first calculation was 2 nautical miles, which is 3 kilometers. Then, now there are better databases that formally have only 1 nautical mile, or even half, I think, a nautical mile. But the physical actual measurements that lie behind these data is based on gravimetry. In most places, it's based on gravimetry. And the physical resolution of that is limited by the depth of the ocean. So it's perhaps 5 kilometers or something like that. So if you go into the database and see what it actually looks like, it's very smooth on the smallest scales, which means that physically the smallest scales are not resolved. So we are just on the limit of resolving the most important scales for this radiation. So clearly, poor resolution of topography is a major uncertainty here. There has been some work lately where I was also a little involved here in trying to use sort of statistical models of this unresolved topography and abyssal hills with parameters using geological parameters of spreading rate and so on to try to estimate the importance of that. And so the result was that probably this could add another maybe up to 20, 30 or even 50%. So it's a big uncertainty, but it's not a dominating thing at least. But so there's not much to do with that until you have, I would say, multi-beam topography for the world ocean. We don't have that today. And then a big uncertainty in the calculation itself is this issue about linearity. The calculations, I mean, the whole method is based on linear method, and that is only valid if you have subcritical slope. Now, of course, the slope is mostly subcritical. On the other hand, this steepest part, where the slope is supercritical, is actually where the radiation is also strongest. So if you calculate the flux, it's maybe up to 1/2 of the flux that comes from points where the slope is supercritical. And there we're pretty much in the dark of what to do, how to calculate this. So this is a big uncertainty. Yeah, I could just say something about this. So the scaling for single supercritical ridge simple idealized examples can be worked out. And if you have just one ridge with some actually rather general slope, it can be shown that the energy conversion goes like the height squared of that ridge. Okay? So that's the same as the linear scaling, in fact. I mean, the linear scaling, by definition, almost, if you look at the linear expression here. Here it is. Of course, yeah, the energy conversion is proportional to slope squared. Here is slope, and here is slope. So it's slope squared, right? And if you have a fixed horizontal scale, it means that it's proportional to height squared. Okay. So that's height squared is the linear scaling. Now, if you have non-linear, well, what's the scaling then? If you have a single ridge, it's still h squared. On the other hand, I think it's a very different thing if you have extended topography with many ridges, and it becomes, so this is the characteristic slope, and if you have neighboring ridges like that, you get a kind of a shadow zone that becomes bigger as the slope becomes bigger. So I sort of speculate that in fact you have a kind of saturation effect, so that instead of this h squared, you have a saturation here. But that, I would say, is the biggest theoretical open problem in the field here. I solved one simple case like that, where you have, which you can solve actually analytically, where you have periodic array of thin vertical walls like that. And the result is that you have a kind of a strange picture with infinite peaks. But you could sort of believe that, this down here is this h square linear scaling, and you can sort of see that you have perhaps an average saturation, but it's still an open problem. Yeah, some remark on future work. As I said, maybe the most important one here is to continue now beyond the generation of these waves and to try to also model the propagation and ultimate breaking of these waves. And also we should start implementing these schemes in general circulation models to parameterize vertical mixing. In most models now this is done in a fairly, I would say, non-physical way, parameterizing vertical mixing. By using these schemes we can have a more realistic modeling of the vertical mixing and thereby also of the deep circulation, because it's really to a large extent governed by this vertical mixing. Okay, thank you. Any questions?
Yeah, in that last point where you are putting that scheme in the ocean general circulation model, that calls for, and the scales you want to be working at are about 10 kilometers or less. That's going to create a big quagmire.
Sorry, I didn't hear the last.
That's going to create a challenge to put in.
Yeah, I mean the challenge, of course, what you're saying, what you're saying is basically that general circulation models, of course, they have two coarse resolution to capture these waves,
right.
And that's why you need to parameterize them. So what the parameterization would you would sort of offline on the side do before you run the model, the general circulation model. You would have separate calculations like the one I've done here, which give you basically a kind of a three-dimensional field, well-founded field of what is the vertical mixing coefficient in different parts of the world ocean, and then you just put in that field into the general circulation model. So the general circulation model would not resolve internal waves. You just have a pattern of vertical mixing that you have calculated offline somewhere else, and then put that into the general circulation model. Of course, topography is not a problem in that respect, because you know the topography. What you don't actually know is one element of this calculation that goes into it is the hydrography, the stratification, which may change because of the circulation in the model. So then you would have to sort of recalculate. If you have a strongly different stratification as as the model is running, then you would need to recalculate this mixing coefficients field, I guess. But if you're fairly close, if you're running fairly close to sort of the observed hydrography, then this should work. Yep. Yes.
Okay. The linear theory breaks down when the topography has this steep slope.
Yep.
Is that because your use of WKB approximation?
Is that what? Sorry.
Is that because you use the WKB approximation?
No, that's a different issue. The WKB, you can actually, I didn't show that here, but there is some recent work that also was done by the same grad student here, which you can get rid of the WKB approximation and take into account the full profile vertically, and then you need to decompose it into vertical modes. But that can be done. But it's still linear theory, and it's still limited by the supercriticality of absorption. So it's a really different issue. So the WKB is not as serious. You can get around that and still do serious calculations. But the supercriticality issue, I don't know how to deal with.
I remember seeing some work using this, still dealing with the linear theory, but using some mapping method to treat the large topography. But then you can only treat a certain kind of topography where you know those mapping functions. Do you know that?
Maybe there is a theoretical, I think it's called a Green's function approach, where you have a contour integral and you can sort of, maybe that is what you mean. I mean, I know a case, I know a method where you can solve the very simplest cases analytically, and you can attack more realistic cases, at least numerically, but very exactly.
Yeah, I'll see. The paper I was referring to is by Leo Marsh.
Leo Marsh?
Yes.
Okay.
Yes, using a kind of mapping method. So you might want to be
yeah.
looking into it.
I think
yeah. It's a linear theory.
Yeah. Okay. Yes.
I just sort of trying to understand what you're getting at in your very interesting analysis. That talking about bottom tidal currents flowing over rough topography, generate internal waves of tidal frequency which propagate horizontally and vertically,
Yep.
become unstable, break,
Yep.
mix the water column,
Yep.
and then must be dissipated as heat. Now, if you think of the conventional model of this four-layer thermohaline circulation, the surface, the Antarctic intermediate, the North Atlantic deep, and the Antarctic water, it's considered to be driven by a combination of heating, equator cooling the poles, and then the variations in the zonal winds creating Ekman effects. Now, what I'm really saying is that at the end of the day, if you're going to have a slow but persistent steady current in the Antarctic bottom water, that has to be driven by horizontal pressure gradients over many thousands of miles. So how does your theory generate those forces?
Yeah, I mean, if you think of the densest water, the Antarctic bottom water here, that's what you mentioned, right? I mean, of course, the flow has to be geostrophic, so there has to be a pressure gradient associated with that. But nevertheless, the fact remains that, you know, unless you somehow remove that, I mean, suppose that you have the existing already this coldest, densest water. The only way you can get any more flow there is if you somehow remove this water and lift it up, heat it somehow, so that it makes room for more dense water coming in. And the only
how can basically energy dissipation into heat?
No, it's not. Sorry, it's not the dissipation. I mean, the heat. No, sorry. I mean, then there was a misunderstanding. When I'm talking about heating, I don't mean the sort of mechanical energy then transferred to heat. That this is heating the parcels. That's not what I mean. I mean it heats the water by mixing cold water from below with warmer water from above.
Okay.
And then that mixes it. I mean, the heat. The conversion of mechanical energy to heat is negligible. That's not the important part of the story. The important part is here. You have warm water, you have cold water. This cold water is so dense that you can never create any denser water at the surface to replace that. But then if you have some mechanical mixing here, you get the water sort of, there's mixing of cold and a little warmer water that makes it a little less dense, and then suddenly the water coming from the surface can be a little heavier and replace that, and so you get the circulation going.
Then what? But how does that drive? Where the pressure gradients come that will drive that water northward?
Yeah, the pressure gradients come from the fact that when you mix that very cold water with a slightly less cold water above, you change the density, and the density, of course, affects the pressure field. The pressure field comes from the density field. So by doing that, you sort of indirectly create the pressure field needed then to get the more, by geostrophic currents, get new water to replace that coldest water.
What's the part I don't understand that?
Well, it's downward diffusion of heat in the tropics and subtropics that produces horizontal pressure gradients in the lower layer. So it's downward diffusion of heat in the thermocline.
Yeah, and the downward diffusion, when you say diffusion, it's actually mixing by breaking internal waves. Exactly. Well, I don't know if you're satisfied. I can't.
I haven't been down there.
Yes?
But just a question is that, so this is one mechanism that can do the mixing. Are there other proposed, what are other proposed mechanisms that can actually achieve similar mixing? Because as you said, it's not completely clear that that what you have is sufficient, or is in the order of magnitude, right? Order of magnitude, but you don't actually know whether it's everything is due to this internal gravity wave internal wave.
I think the general consensus is that in some way or another, it's really internal waves that do the mixing. The big question is, what are the sources of these internal waves? And most people agree that tides is probably the biggest source, but there are also other sources, and the relative importance of these various sources is still under it's research. And I would say the main candidates are, the first one is tides, the second one is lever waves that you talked about before, and it's also internal waves and topography, but they're not created then by tidal currents, but by geostrophic currents. And the geostrophic currents could be strong, persistent currents in boundary currents, or But for the most part, they would actually be from eddies. So if you have baroclinic eddies in the ocean, they have a signature down to the bottom, and if there is, and these are slower than they have a much longer, slower time scale than the tides. So it's a different kind of internal waves, but it's still internal waves excited by then eddy flows near the bottom, and they also break, but they have shorter time. They have much shorter length scale, for instance. So that's called lee waves. So that's another part, tidal internal tides, lee waves, and the third would be then inertial waves created in the mixed layer by atmospheric winds and storms and things, and then waves propagating downward from the mixed layer. That's the third important. Well, and maybe I would say there is one more candidate which is very, very speculative, and that is what happens with eddies. Let's say baroclinic eddies, baroclinic instability of eddies. Now, what is the final fate of the energy in these baroclinic instability eddies? Do they excite internal waves or not? Now, I think it's called loss of balance, and this is a big theoretical unknown. I would say, but most people believe that you don't actually get an internal waves in that way, but there are, many people who also actually believe that actually, even for this baroclinic instability, there could be a strong excitation of internal waves. But this is completely in the dark, I would say, in that mechanism. I think these are the main ideas of these internal waves. But I think there's no big question that the mixing is done in some way or another by internal waves.
So if there are no other questions, let's thank our speaker again, and then we have lunch in the
So where's the switch? This is
Those are dangerous. We tell my mom about it like a year ago.
This whole region one other device varies in the atmosphere. Ocean. You draw a vertical profile, curves. This is in the next layer up here, maybe just the temperature like this. Different things in yeah, it really is. And the stratification just gets higher and higher, and the stratification seems to be maximum in this area, typically. Not in here. Stratification is not maximum. It's getting lower. Classically, in all the texts, from the bottom of the sixth layer down to about the middle. Well, very spatial. 5 kilometers. Better criteria. Well, we can look at the visor. We should look at that carefully. The visor frequency is very high up here, and it drops off. So we should plot that carefully. But I don't know any criteria. You can ask Chris. I don't think there's a simple criteria like the visor is some value.
I know. Well.
Be useful. Well, if we can set a value here, look at the visor frequency here. Below here, the visor gets even lower. It's like 0 down here.
Okay, yeah.
We can see what that value is.
like an
So
hourly
Weissler
rate
goes
or
from
an
some
hourly
value up to
Okay.
the maximum.
So
we can look at that on the plot. Those are nice data. They're very high resolution and they're vertical.
Yeah.
So we can look at the Weissler profile down here.
There's a movie like
Look at the data that we have.
Yeah.
Oh my God, yeah, Bob's gonna be so angry. Yeah, I know.
Very low.
Yes, but if you see
But
the
it gets
temperature
less,
profile-
it gets lower. When it reaches a minimum here, then it gets almost zero down here.
Yes.
But we can, I'll plot the Weissler profile very carefully, and we can look at it. But that's a good question, exactly where it is. What I expected people to do is look at the curve and say, this is kind of a dumb flat. But it's really from here, the bottom of the deepest seasonal mixed layer, down. And, so, if somebody looks at it like a student, we say, oh, this is good, which is reasonable. And we should look at the Weissler here, see if there's a characteristic number. Because this doesn't vary. And usually you'd find the abyssal depths is this region where the Weissler is constant and nearly dead zero. That's why I don't like his results, because they're very sensitive to N, and that's so low. And down here, even in the main thermocline, it's variable. Anyway, his results are very sensitive to N. And those wave drag results that he had were very sensitive to NB. Weissler down here at the bottom. That's extremely low. So, he's got to look at the data. I don't know what kind of data. So it's sensitive to N. If he's got good values to N, you can use them. But you need decent CPD data to do that. Maybe he hasn't. Maybe he's using those data. Yeah, I thought the talks were nice. So, why don't you go ahead and post homework 3? So, in the homework 3 folder, just post it.
Yeah, and so for the thermocline, I will get you a random number from bottom of mixed layer.
Bottom of the seasonal mixed layer
to the
you can look at the curve to abyssal depths, okay, at the top of the abyssal layer. The layer, so it goes like this, and it goes down. If you look at cartoons in lots of books, thermocline goes like this, and then down. So it's the top of the, just where it starts to
keep nearly constant.
right. Usually you define abyssal depths, thermocline, that's a good question. I think I should
you.